So, okay, so we've been talking about the CCFT, the continuous Fourier transform. Um, and so last time we had ascertained that you should think of this as being a transform from L1, the real line, into the space C00 on the real line of functions that are continuous, which is that 0, and which decay to 0 at infinity, which is that 0. Okay. All right. So last time we discussed basic properties of this transform. And now what we're going to do is talk about inversion. And the story here, interestingly, is very much like the story for inversion of the CDFT. And so therefore, I'm going to go through it sort of quickly. Okay. And the first step, just like it was for the CDFT, is just to make sense of the fact of invertibility, and that is that FCC is injective. Okay, and so we went through and we proved this for the CDFT. You can make a proof for the CCFT, which is rather similar to that for the CDFT. There's a few technicalities that you have to deal with because the domain on which the time domain in this case is not compact, whereas it is for the CDFT because essentially things are periodic. So the domain is really just some compact interval from 0 to t. But in spirit, it's very similar to the proof for the CDFT. So I'm not going to dig into it here. All right. And so just like for the CDFT, you want to talk about what is its inverse. Okay. Okay, so you want to find a left inverse. Okay, so a left inverse should be some kind of a mapping, and I'm going to write it like this. Okay, such that, and the way you should think about it is that the inverse recovers f from its CCFT. Okay, so what that means is if you apply this inverse to the CCFT of something, you get that thing back again. All right. And the story here is rather similar, and I talked about it at some length for the CDFT. So let me just sort of remind you of the main features here. So the first thing we're going to do is we're going to propose what seems like a natural left inverse. Okay, it's going to be the analog for the CCFT of the Fourier series. Okay, and unsurprisingly, it's going to be the Fourier integral. All right. Then we're going to assert that this thing is a poor inverse. Right. So in other words, it has poor convergence properties. So what you then try to do is you try then to find conditions on a function here so that this inverse does satisfy this property. Okay, so you have some subset of signals here for which this is true. Okay, what you mean by this also is going to involve convergence because for the CDFT, we had convergence of Fourier series. Well, here we're also going to have a convergence issue, and then now it's going to be convergence of some integral. Okay. All right. So, so first, proposed inverse. Okay, and this is just going to be by analogy with Fourier series, is how we're going to talk about this. I'm not, in other words, our motivation is just going to be by analogy. Okay. And so if F, so let me just write these things side by side just to make sure we understand how they're similar. Okay. All right, so we have the CDFT data on the left and the CCFT data on the right. All right, then and then the CDFT looks like this, and the CCFT looks like this. And so this is evaluated at some frequency nu. So, and then we had the Fourier series, right? And the Fourier series looked like this. Okay, so it was a linear combination, infinite linear combination of the harmonic functions, and the coefficients are just the coefficients given to you by the CDFT. Right now, for the CCFT, the summation will be replaced by an integral because the frequency variable is continuous. But other than that, we're going to take the same thing. Like so. Okay, and so this was the Fourier series. And this is the Fourier integral. Okay, and so, you know, these things as they are written here and here are imprecise, because here we haven't thought about convergence of this infinite series, and here we haven't thought about integrability of this function. Okay, and in fact, this function generally is not integrable. Right. Okay, so what did we do for the CDFT? Well, for the CDFT, we considered partial sums. Okay, so the partial sums for the CDFT were a sum from n equals minus n to n f CB of f. Now, the partial integral, if you want to talk about it that way, for the Fourier integral is going to be an integral from, let's say, minus omega to omega FCC of f of nu e to the 2 pi I t d nu. All right. Now here, this was well defined simply because it's a finite sum. Okay. Here, the integral is also always well defined. And the reason that it's always well defined is that we know that this is a continuous function of nu. Okay, so what we're doing, and of course this is too, and so the integrand therefore is continuous, and so we're integrating a continuous function over a compact domain. Continuous functions are always bounded on compact domains, and so we can conclude that the integral always exists. Okay, so there's no problem with what this partial integral means. Okay. All right, and so what we did was we argued, or we didn't even argue, I just wrote it down, that there was a formula for this partial sum, and that formula was 1 over t, integral from minus t over 2 to t over 2, f of t minus tau d per t of tau d tau. Okay, and so therefore, based on that formula, I denoted the partial sum here by d per t n f. Okay, t, right? Now, a similar formula holds here. And so d per, there's a formula for d per, and it's sine 2 and I think, I'm forgetting the exact formula, but I think it's 2n plus 1 pi t over t over sine pi t over t. I believe that's the correct formula. All right, and then so there's a similar formula that holds here. Okay, and that formula involves another kernel function. So this was the Dirichlet kernel. Okay, and so here's the formula for it. And so here we're going to get another kernel function, and we're going to get a convolution. Okay, so this quantity here is exactly equal to the integral over r of f of t minus tau d omega of tau d tau. Okay. All right. And what's d omega? Okay. And so this is the periodic Dirichlet kernel. Okay, and here d omega of t. Oh, so sorry. Let me make this exactly symmetric. Oh, so I apologize. I made a mistake here. Yes, sorry. Let me fix that up. Okay, so this quantity is equal to this. Okay, and this thing here is the Dirichlet, periodic Dirichlet kernel. Sorry about that. Okay, and so here we're going to denote, and so again, let me write it so that it's symmetric. We're going to denote this thing, but because this is a convolution, okay, we're going to denote this thing by d omega f of t, okay. And so, sorry, again, carrying on my same error, this thing is the periodic Dirichlet kernel. Okay, and the periodic, the aperiodic Dirichlet kernel is d omega Okay, so d omega of t is equal to, okay, so let me get the data right. So it's sine 2 pi omega t over I t, okay? And this is the aperiodic Dirichlet kernel, also known as just the Dirichlet kernel. Okay. All right, so this, so first of all, notice that this integral for every fixed omega, okay, and so this omega comes from the limits of the partial Fourier integral, just like the capital N here comes from the limits of the partial sum for the Fourier series, okay? So for every omega, this function is a continuous function. So the value of this thing at 0 is just 2 omega, okay? So this is continuous, this is an L1, so that integral, so it's a L1 function times a bounded function, so that integral certainly exists for every t. Okay, so there's no problem defining that integral. And this is to prove this equality here, just like this equality here, this one's actually easier, but it's just a direct computation. Okay, so you can look at the posted course notes for that, okay? And so the idea here is you have this this really quite spectacular symmetry between the CDFT here and the CCFT here, okay? And so we're going to build on that to give results that are analogous for the Fourier integral as those we gave for the Fourier series, okay? And you can see here that the kernel functions for small n's, and if you assume an appropriate relationship between omega and n, for small t, these are approximately equal to each other just because this is approximately pi t over t, okay? All right, so these things, the kernel functions look the same for small values of t, okay? which is a will be important for pointwise convergence, which is what we'll talk about shortly. Okay. Okay, and so so thus, just as we studied convergence of Fourier series, by considering the sequence of partial sums d per t and f, okay, we study the convergence of Fourier integrals by considering the family d omega f omega n. Okay, and these are, the family of partial integrals in the same way that these are partial sums, okay? All right, and so what we want to do here, so we took the limit, we looked at the limit as n goes to infinity, of course, and here we're going to be looking at the limit as omega goes to infinity. Okay, so first of all, one generally does not have convergence. Okay, and so we had this discussion that we engaged in about Fourier series, about divergence of Fourier series, and I gave you kind of a historical discussion. Kolmogorov's proof of the existence of a L1 function whose Fourier series pointwise diverged everywhere, divergence of the Fourier series in L1, divergence of the Fourier series on a set of measures 0, even for continuous functions, okay? So convergence, all those assertions that we made there about convergence of Fourier series apply to Fourier integrals, okay? So C discussion of divergence of Fourier series. Okay, so things don't get better for Fourier integrals. Okay. All right, so it's maybe also, since this gives us an opportunity to talk about both of these things at the same time, it kind of provides additional context about why the convergence properties of the integrals and series are so poor. So here, okay, the coefficients of the Fourier of this sum are the coefficients of the Fourier series, and here the integrand is composed of harmonic functions but multiplied by the CCFT of our function. So what do we know about these coefficients, and what do we know about this function of nu? Well, here all we know is that it decays to 0 as n goes to infinity. Right, but it can decay to 0 very slowly, okay, which is what causes the problems with the convergence of this series. And here, as nu goes to infinity, we know that this continuous function goes to 0, but we don't know anything about the rate at which it goes to 0, and so that's what causes the problems with the existence of that integral. Okay, all right, and so you need conditions on f that are going to guarantee that this thing behaves in a nice enough way that you get some kind of convergence. Okay. All right, good. So the first thing we'll talk about is pointwise convergence of Fourier integrals. Okay, just like we talked about pointwise convergence of Fourier series. Okay. Right, so the idea, just like for Fourier series, is you want to derive conditions on f, which ensure pointwise convergence of its Fourier series. Okay. And just like for Fourier pointwise convergence Fourier series, there's a main sort of pointwise convergence theorem, which gives you results that you can use. Okay, so for f in L1, T0 at some time, because we're talking about pointwise convergence, and for some value s, okay, the integral converges to, okay, the following are equivalent. Okay, so the first is convergence of this family of integrals. Okay, so integral from minus omega to omega cc of f. Okay, that nu. Okay, and so it's pointwise convergence at t naught. So this means 2 pi I nu t naught d nu is equal to S. Okay. All right. So just to clarify, when I take a limit here as omega goes to infinity, this is equivalent to saying that if you take any sequence of omegas that diverges monotonically to infinity, that this limit should equal S for that sequence. Okay, so you can turn convergence of this family of integrals parameterized by a constant omega into convergence of a series, but it should hold for every series. Okay, or you can say, just in the way that you do for convergence of infinite series or sequences, you can say that there exists an omega naught such that, okay, so the error is less than epsilon for omega greater than or equal to omega naught. Okay, so you can convert this into a statement like there exists a capital N so that some error is small for index is larger than N. Well, you can do the same thing here, but the index will be some real number. Okay, so anyway, this limit can be interpreted in multiple ways. All of them, I think, sort of natural in the sense, so natural that probably you don't think about it. Okay, good. All right, so now what we're going to do is we're going to, just like we did with the corresponding statement for Fourier series, is we're going to convert this into a statement involving the Dirichlet kernel. Okay. Okay. All right. Now, so this requires discussion. All right. So if you look back at how we proved this for the Fourier series, okay, so there's obviously so obviously this equality is at play here. Okay. And in fact, for Fourier series, we use the fact that the integral from minus t over 2 to t over 2 of the Dirichlet kernel was equal to 1. And I forget if there's a 1 over t there. Maybe there was. Okay. Okay, so there was a fact about the integral of the periodic Dirichlet kernel. Well, there's a corresponding fact about the integral of the aperiodic Dirichlet kernel, but okay, it's not going to be just that the integral over r d omega dt is equal to 1. Okay, it's the conditional integral. All right, because this function, this integrand, the Dirichlet kernel, is actually not integrable. It's conditionally integrable, which just means that if you go limit from integral from r to r, and then let r go to infinity. Okay, so we talked about this kind of notion of conditional integrability when we talked about integrability a long time ago, and so this thing equals 1 is a conditional integral, and so therefore, in this statement, I have to use the conditional integral. Okay, because what I've done is I've gone, s times 1 and pulled this s inside the integral using the fact that the conditional integral of this is equal to 1. But the price I pay for that is that this is not the integral, the normal Lebesgue integral now. It's the conditional Lebesgue integral. Okay. All right, and that subtlety didn't come up for Fourier series because for Fourier series, we didn't have conditional integrability of the kernel. We had actual integrability of the kernel. Okay, a little technicality there. Okay, and now, just like for the Fourier series, what we do is we localize this, okay? Right, and so this integral, which now sort of accumulates all the data about f's, with the Dirichlet kernel over all of R, because as omega goes to infinity, the Dirichlet kernel has the same properties as the periodic Dirichlet kernel, in that it kind of becomes very spiky around 0. Okay, so omega, small omega, looks something like this. Okay, and as omega gets larger, it looks something like that. Okay, and then it gets spikier and spikier as omega goes to infinity. Right. So just because of that behavior, this integral over R can be concentrated around 0. Okay, so the limit as omega goes to infinity integral. And now this is no longer the conditional integral, because I'm only integrating over this compact domain. From minus epsilon to epsilon. Okay. All right, so I've already sort of indicated how the proof goes here. By first pointing out that the conditional integral of the Dirichlet kernel is equal to 1, and so you pull this inside the integral. Okay, so that gets the equivalence of 1 and 2, and then the equivalence of 2 and 3 follows from the Riemann-Lebesgue lemma, just like it did for essentially by the Riemann-Lebesgue lemma, just like it did for Fourier series. Okay. All right, good. All right. And now this localization property that you see here, okay, that this integral is actually only being done over a little interval around t naught, okay, which means that you're only looking at values of the Dirichlet kernel for small t's, okay, and the fact that these kernels are approximately equal to each other for small t's, okay, setting omega and n so that things match up. This is why we're going to get results for pointwise convergence of Fourier integrals that exactly mirror those of pointwise convergence for Fourier series. Okay. All right. All right. So now, okay, we use the previous to give a list of sufficient conditions for pointwise convergence of Fourier integrals. Okay, so I'm just going to quickly list these. Okay, so there's Dini's test because again they do look just you could write them down if you know the results for the Fourier series. They're more or less exactly the same with the obvious modifications. Okay, so if f is in L1, and T naught is some number of time that you're pointwise converging at, then if the integral from minus epsilon to epsilon f of t naught minus t minus s over t dt is equal to, or sorry, is bounded less than infinity. Okay, so the idea is that over epsilon to epsilon, this thing is in L1. Okay, all right, so if this is true for some epsilon positive and some s complex number, then the Fourier integral converges to s. Okay, so then this family, sequence of partial integrals and so, sorry, this is evaluated at t naught. Converges to s. Okay, so that's Dini's test. So there's an alternate version of Dini's test, and we talked about this for Fourier series as well. And you replace now, it's the same statement, except you replace this integral with an averaged version, like so. So it's f of so it's f of t minus t naught plus f of t plus t naught minus s over t dq plus infinity. Okay, the rest of the statement is identical. All right. All right, and just like for Fourier series, you can use Dini's test directly to prove convergence of the Fourier integral at points of differentiability. So if f is in L1, and is differentiable at t naught, then this family of partial integrals converges, and moreover, the convergence is to f. Okay. All right, and then there's Dirichlet's test. Okay, and so this says that if f, and so you always have to have f in L1 because the Fourier integral has to make sense, which means that you have to, the Fourier integral is defined in terms of the CCFT, so you always have to have f in L1. And in Dirichlet's test, you have some limits that need to exist. So f of t naught plus, okay, so the limit as t approaches t naught from the right, and then also the left. We define these things for the Dirichlet test for the Fourier series. And then get derivative conditions as well. Okay. Okay, then again, you get convergence, but you get convergence to something predictable. Namely the average of the left and right limits. Okay. All right. Then there's examples, and I'm definitely not going to go through the examples laboriously because we did that with the Fourier series, and the examples are kind of the same, right? Or at least they have the same character. All right, so let's look at this thing. Okay, so it has a value 1 between minus a, and 0 otherwise. Okay, and so you get pointwise convergence to this function. Okay, so now at points of differentiability, which is every point except minus a and a, the Fourier integral converges to f. Okay, and so 0 here, and oops, 1 here, and these points are omitted from both of these. Okay, and at this point, it converges to the average of the left and right limits. So this is 1, this is a half. Okay, so you get pointwise convergence like so. Okay. Then you can look at something like this. Okay, let's call this G. And so you get pointwise convergence to G again. Okay, and now to get this, you can use, all right, so for this version up here, you use the derivative test everywhere except at the points of discontinuity, and at the points of discontinuity, you use Dirichlet's test. In this example, you can use Dirichlet's test. Well, first of all, you have the differentiability, which holds everywhere except these points of discontinuity, or sorry, not discontinuity, but discontinuity of the derivative. And at the points of discontinuity of the derivative, you can use Dirichlet's test. Okay. Right, so the pointwise convergence tests work because they're only local, right? They only involve the character. All of these tests, right? They only involve the character of the function nearby t naught, and so they work exactly the same for Fourier integrals as they do for Fourier series. Okay. Uniform convergence of Fourier series. Okay, so again, we're going to concentrate on giving results which are analogous to the results that we gave for the Fourier series. Okay. Okay, so if f is in L1 and if the CCFT of f is in L1, then the following statements hold. Okay. The first statement is that this converges, this family of functions converges uniformly to a continuous, in fact, it's uniformly continuous, to a continuous G. Okay. And f of t is equal to g of t for almost every t. All right. Now, this was relatively easy to prove for the CDFT. We used the Weierstrass M test, and we had we had that CDFT was in little L1, okay? And so we could use this Weierstrass M test or convergence of infinite sums of continuous functions, okay? The proof in this case is not the same, and it's quite different and a bit harder, all right? But the statement looks the same, which is already quite interesting, okay? And so, but maybe let's, you have the Weierstrass M test kind of gave you the continuity for the CDFT. Let's think a little bit about continuity for the CCFT, okay? All right, given that the CCFT of F is in L1, okay? All right, so here, again, because the CDFT was in little L1, we use the Weierstrass M test on that infinite series. Okay, now we know, or we're assuming, that the CCFT of F is in big L1, okay? So if the CCFT of F is in big L1, then this thing looks rather the same as the CCFT itself, right? But rather than applying this construction to F, you're applying it to the CCFT of F. And one of the conclusions we got out here was that if F was in L1, then this thing was a continuous function of nu, and in fact was uniformly continuous. And so by the same reasoning, because the only change here is a minus sign, right? And the minus sign doesn't have any material effect. And to see that, all you need to do is just change nu for minus nu. Okay, then you put a minus here and a minus here, right? So if F is in L1, then flipping F about about 0 also gives you something in L1, so that doesn't change the conclusions. Okay, so the point is that if the CCFT of F is in L1, then by the same arguments which give continuity here, will also give continuity here. Okay, so that's, you can see kind of that the continuity there is to be expected. Okay. All right, now, just like for the CDFT, this is a very elegant result, okay? It has a nice set of hypotheses, and it gives a very elegant conclusion, but it's difficult to verify because you have to verify that the CCFT of F is in L1, and you would like some maybe conditions on F, which would guarantee that this holds, okay? And just like for the CDFT, there is such a statement. Okay, so it's elaborate, so that's what it is. All right, so you take F, which is in C0, and if there exists an F prime, okay, and so again, F prime is not necessarily the derivative of F, but F is the indefinite interval of F prime, okay? Okay, so F has to have some properties. And so this will remind you of the differentiability result we gave for the CCFT. There's one important difference. Okay, so it's piecewise continuous on any compact subset. Okay. F prime has finitely many discontinuities. Okay, F prime is in L1, intersect L2. Okay, and this is the additional hypothesis that we need. And the reason is, if you look back at how we proved the analog of this result in the case of the CDFT, we used Bessel's inequality, which is an L2 thing, a Hilbert space thing. And so that's why you need this here. Turns out if you dig into the proof of that, that's where that shows up. Okay, and then the obvious relationship between F and F prime. Like so. Okay, so if all of that is true, then okay. This converges uniformly to F. Okay. All right. And so you'll notice here that I didn't assume that F is in L1. And it turns out that that's because this fact, along with this fact, actually implies that F is in L1. Okay. All right, good. So there's uniform convergence. Examples, and again, the examples are kind of the same as what we had for uniform convergence of the CDFT or for Fourier series. Okay, so let's look at the two examples that we had above. Right, so 0 out here, and then 1 in there. All right, so this does not converge uniformly. And it's a tiny bit more subtle than it was for the CDFT. So for the CDFT, because everything's on a compact interval, there's all kinds of statements that you make there that are that follow from elementary things. Okay, so what you'd like to kind of have be going on here is that the discontinuity at these points prohibits uniform convergence, okay? But the domain here is unbounded. So you do have to be a tiny bit careful, but nonetheless, it's true that because you have pointwise convergence of this family to a discontinuous limit function, that does prohibit uniform convergence. Okay. All right. And then this one. Right. So here we have uniform convergence to G. Okay, and the reason here is just exactly by the corollary. Okay, so you can find an F prime, okay, and what will G prime be? Okay, so G prime here is going to be, well, if it goes up to the point 1 here, then the derivative is going to be So as a gets large, the derivative will get small. And so the value of the derivative here is going to be 1 over a. And then here it's going to be minus 1 over a. Okay, but the point is that the derivative g prime, okay, satisfies these conditions. Right? And so the corollary gives you uniform convergence. Okay, good. All right. Okay, so again, wrapping things up by analogy with Fourier series, you also have a Gibbs phenomenon. But now for Fourier integrals. Okay. And I'm not going to go through the entire construction again. I'll just say just like for Fourier series. Okay, and the reason is the Gibbs phenomenon has to do with pointwise convergence, and pointwise convergence, as we know from our sort of master theorem on pointwise convergence here, and especially part 3, pointwise convergence is a purely local phenomenon. Okay, and so because pointwise convergence for Fourier series and Fourier integrals essentially is the same because the Dirichlet kernels agree for small t. That's why the Gibbs phenomenon just looks the same. Okay. All right, you also have Cesàro convergence, which is kind of an averaged form of convergence. And so remember so again, I'll just sort of do this by analogy with the CDFT, just to emphasize the similarities between these things. So for the CDFT, you average the partial sums of the Fourier series, which means that you go sum j equals minus n to n. You take the little nth partial sum, and that's CD. Okay, to I and t over t, and then you average those from n equals 0 to n minus 1. And then because you're averaging, you divide by n. Okay. And this turned out was these average partial sums were given by a convolution formula, okay? And that was 1 over t, integral from minus t over 2 to t over 2, f of t minus tau, and then the periodic Fourier kernel showed up here. Okay. And then we defined this thing to be using the fact that it's like a convolution. We wrote this partial sum like that. Okay. And the Fourier kernel was sine of n squared I squared t squared, and that's possible. I'm getting some things wrong here, but in sorry, I'm going to write it down below here. Also run out of space. Okay, so sorry, let me try to get that right. So it's sine squared of pi n t over t, like that. Sorry, I was definitely wrong before. And then it's here, it's sine squared of pi t over t. Okay, so I believe that's correct. All right, and so this was the periodic Fourier kernel. Okay. All right, now, again, by analogy, I'm going to take the averaged Fourier integrals. So now I'm going to integrate from minus omega to omega, FCC of f of nu e to the 2 pi I nu t dt. Okay, then I'm going to average that over capital omega, divide by omega to average. Okay. All right, now this, again, by a computation, all right, so this equality here is not obvious, and this one will not be obvious either, okay, although it is easier to prove than the summation version, okay? But this is, again, a convolution of f with the Fourier kernel. But now it's, of course, a different Fourier kernel, not the periodic one. Okay. All right, and so because that's a convolution, I write it as sort of convolution-y notation, like so. Okay, and then the continuous Fourier kernel is, okay, so it's sine squared pi omega t over pi squared omega t squared. So, right, and this is the aperiodic Fourier kernel. Okay. All right, and so again, you get this lovely symmetry between the two transforms here, okay? For one thing, and then the other thing is you get this lovely appearance of these various kernel functions that show up here, the periodic one here and the aperiodic one here, and they rather look the same. You know, for small t's, they look, kind of exactly the same, again, assuming some relationships between n and omega so that things make sense. So you get these really rather deep connections between kernel functions and inversion of the transform and so on. Okay. All right, and so then just like for the CDFT, you get very nice convergence properties for these averaged partial integrals, okay? Okay. So if f is in LP, then this family of averaged partial integrals converges to f in LP. Okay. Now, this fact really just follows because the Fourier kernel is an approximate identity. Okay, so we talked about approximate identities and how approximate identities give us exactly these kinds of convergence and approximation properties. Okay. All right. So if f is in C0 bounded of okay, then f omega f converges uniformly to f on compact intervals. Okay. Okay, now if f is uniformly, so here I required bounded and uniformly continuous. So here I'm going to require that it be uniformly, I forget what I think I said, I made a mistake there. So bounded and continuous, okay? So here I'm going to require bounded and uniformly continuous. So unif BDD means bounded uniformly continuous. Then you get uniform convergence on all of R to F. Okay, so again, this result is a approximate unit result. Okay, and the result here has to do with the fact that uniform convergence is somehow tightly connected to Fourier integrals, and the reason is that when you take the CCFT of something, what you get is not just in C00, what you get is something that's in C0 unif 0, so it's uniformly continuous. And because the Fourier integral is essentially the same as the Fourier transform, the inversion on continuous functions is only going to work well on uniformly continuous functions. Okay. All right. And so, just like for the CDFT, you get these much nicer convergence properties when, excuse me, when you use not the Fourier integrals, but the averaged Fourier integrals, all right? But again, just like for the Fourier series, there's a price you pay, and that's the rate of convergence, okay? So you may get stronger convergence theorems, but in practice, if you're trying to work with inverses, this might give you slow convergence, okay? All right, so I think I'll stop there for now. And the next topic is going to be the L2 CCFT. And one of the things we're going to see is that has some subtleties that you have to bookkeep in ways that we didn't have to do with the L2 CDFT.